Aloha everybody. My name is Ehsan, the PhD student at the Institute for Astronomy at the University of Hawaii. In this presentation, I'm going to talk a little bit about the project I've been running for past couple years and show you how we are going to incorporate the measurements you have made in our analysis. First of all, I would like to thank my advisor, Brent Tully, and all of my other collaborators, as well as the University of Hawaii undergraduate students and the amateur astronomers who helped me with some of the tedious and time-consuming manual tasks. The main goal of our research is to map out the density structure of matter in the local universe. To do so, we need to measure the relative velocity of galaxies known as peculiar velocities. However, as we observe galaxies from the Earth, the measured radial velocity is a superposition of the global Hubble expansion rate and the peculiar velocity. This means that to extract peculiar velocities, we need to measure the physical distances of galaxies and then subtract the resulting Hubble expansion rate of each galaxy from the measured radial velocities. But the question is that how we measure the distances of galaxies. There are many different methods to measure distances, and each one only works with specific objects. In this research, we focus on only spiral galaxies. The spiral galaxies are flat and have disky features, and they are spinning around their center. There is a well-known relationship between the absolute luminosity of spiral galaxies and how fast they rotate. In astronomy, this famous relationship is known as Tully-Fisher relationship. Intuitively, one expects that more massive galaxies to be brighter and rotate faster. If we measure how fast the galaxy rotates, then we can estimate its absolute luminosity and compare it with its apparent luminosity that we observe. The difference between absolute and apparent luminosities leads us to the actual distances of galaxies. With all of that in mind, to achieve our goal, we need to measure two different quantities. First, we need to measure the rotation velocity of galaxy, which results in their absolute luminosity if we use the Tully-Fisher relationship that connects the rotation velocity and luminosity. Second, we need to measure the apparent magnitude of galaxies, which together with the obtained absolute luminosity from the previous step, it gives us distances to galaxies. First, I am going to talk about how to measure the rotation velocity. Spiral galaxies are late-type galaxies with a lot of atomic hydrogen gas which undergoes star formation. The hydrogen atom consists of one electron and one proton. Each hydrogen atom can be found in two different states. In one state, both electron and proton have the same spin directions. And in the other state, electron and proton have opposite spin directions. The opposite spin direction has a slightly lower energy level, and the transition from high to low energy states produces radio emission that can be observed at 21 centimeter. Some of these 21 centimeter emission is blue shifted and some red shifted as the consequence of the rotation of spiral galaxies. This means that the 21 centimeter emission line is broadened due to rotation. Faster a galaxy rotates, the broader the 21 centimeter line is. In addition to the rotation, the inclination of the galaxy can change the broadening of the 21 centimeter emission line. If a galaxy is totally face on, the observer doesn't see any rotation, and the broadening factor is minimal. As the inclination increases, the 21 centimeter line width increases. This means that in addition to the radio observations, we need to measure the inclination of galaxies. The H1 21 centimeter profiles have been already observed and the line widths have been extracted. Thanks Ellen and her collaborators for pushing these observations to measure the distances of more spiral galaxies. The radio data used in our research comes from different radio telescopes like Arecibo, Green Bank, Nancy, Parkes, and others. The second ingredient that we need to measure distances is apparent magnitudes of galaxies, or the amount of light the observer receives. The farther away a galaxy is, less luminous it appears. To do photometry, I use the infrared images provided by WISE Space Telescope in 4 different bands. One of the advantages of WISE is that it covers the entire sky. I also use Sloan data in optical bands that only covers the northern part of the sky, as well as Pan-STARRS images, which are mainly used to measure the inclinations due to their higher resolution. In this ATOF equatorial plot, you see the all-sky coverage of all galaxies in our sample. For almost 78% of them, we have optical STSS photometry data, and for the rest, we are solely relying on the WISE photometry. This solid curve shows the plane of the Milky Way. This plot shows the distribution of galaxies in the currently available Cosmicflows 3 data catalog. The green points mainly cover the southern part of the sky. My current study mainly focuses on the northern part of the sky, where we have both radio and optical data. This study complements the previous Cosmicflows 3 catalog. These cones along the x-axis show the planes that are obscured by the Milky Way. The absolute luminosity, or the mass of spiral galaxies, is related to their total rotation velocity, but what we really get from the H121 centimeter line widths is the observed rotations that has the projection factor dictated by the galaxy inclination. Therefore, it is important to measure the inclination of galaxies with high accuracy. In order to measure the inclination of 20,000 spiral galaxies in our sample, we have designed an online graphical interface. You might be familiar with how it works. The idea is that users compare unknown galaxies with a bunch of standard galaxies with known inclinations. Then they can move the target galaxy, which is highlighted in yellow, to the right or left by dragging and dropping. To estimate the inclination of each galaxy, user goes through 2 steps at most. In step A, the difference in the inclination of standard galaxies is 5 degrees. Once users narrow down the approximate location of the galaxy, they have the chance to increase the measurement accuracy in step B, where the inclinations are 1 degree apart. Therefore, at the end, we expect users to estimate the inclination of an unknown galaxy with the accuracy of almost 1 degree. So far, all users together have spent more than 1,100 hours on this project. About 5,000 galaxies have been already rejected due to the poor quality of images or bad H1 profiles, which made them bad candidates for the distance measurements. For those galaxies that have not been rejected, I have made sure that there are at least 3 different measurements done by different users. This increases the accuracy of the final results as we use the median of all measurements. As I have written in the Inclination Zoo blog, there are very interesting instances where 2 galaxies are merging or one is overlaying the other. It is critical to pay attention to the H1 profile when they are available. As you see in this case, a second face-on galaxy is overlapping the main galaxy. And also, we found many mergers and other bizarre examples in our catalog where we cannot measure their distances using the Tully-Fisher relationship. At this time, we have enough information and data to move on to the next level of analysis and prepare the next generation of distance catalog using which we can find more local galaxy structures like Laniakea. Hopefully, by the end of summer 2019, this catalog is ready. I would like to thank all of you who have already participated or will participate in this project. With more measurements, of course, we can better understand the nature of uncertainties and minimize them. All the final products and data catalogs would be available to public through the Extragalactic Distance database. I appreciate all of your comments and suggestions that help us to improve this process. Thank you all again for your time and considerations. Mahalo.